All right, we'll start the camera a few minutes early today.
Hello.
That's right. Carson's not this class.
I offered for him to join us. He was short, his credits weren't working, and he was gonna have to take something else, and I said, well, you take strength materials, and he specifically avoided it, so.
I think he has contempt areas.
I just feel like you would have liked this class.
It's one of my favorite classes.
It
One of
makes
my 5
sense.
favorite classes.
It's one of my 2 favorite classes.
Okay. What are we on? We did that one.
You really like controls?
I like controls. I've been enjoying it.
It's not too bad. I feel like Carson, though, like every 2 seconds he just doesn't understand. And I'm kind of convinced it's because he didn't watch those videos.
Yeah.
But there's only videos sometimes, right? There's not always videos, right?
No, there were 2 days where Gagnon didn't come in, so he videotaped the class, or videotaped himself. And I don't think Carson watched those videos, so he's really confused. But
Yeah, that'll do
also,
it.
I discovered that some people are making very low scores on those speedies. Like Chris, who said he finally got points today, which makes me feel better about getting half credit on almost all of them.
On what? Speedies?
He calls them speedies because he was going to call them quickies, and then he decided that was a bad idea.
Right.
But they're like
They're really
mini
quick
quizzes.
tests. It's basically concepts, so it's,
Yeah.
if you know the concept, you can do this problem in like 2 seconds.
But if you don't know the concept,
It
then
takes
you're as well.
forever, yeah, right.
Yeah, I actually like them a lot. It doesn't always work out because sometimes we spend a lot of time going over them because if everyone does poorly, then
Yeah.
Right.
Well,
Which-
that and on not the one from today, but the one from yesterday, he made a mistake. He like wrote the question quickly, he made a mistake in his analysis, and then couldn't explain it to us the right way because Josiah had done it a totally different way than what he was expecting us to do.
Mhm.
And so Josiah came up with a totally different answer that should have resulted in the same answer. So he spent the whole class trying to figure it out, then gave up and had 10 minutes of something else.
So, but he realized that the underlying issue was a misstatement of in the problem.
yeah, he
Well,
fixed it in
That's,
post.
and that's why the 2 answers were different.
Yeah.
Well, it wasn't in the question, it was in integrating. He didn't integrate properly.
Oh.
Was it an integration? I thought it was like an earlier thing that carried over.
Well, like,
Well, whatever it was. It doesn't matter because it's 301 and, you know, I don't want to rob you of your strength and materials.
Oh,
So,
right.
What is this?
you're
That class is-
I'm telling you, man, you know.
You can sit over here with
Open spot over
us.
there.
Oh, no.
All right.
Wow.
All right, new pen today, new pen.
I thought it was gonna go out. Which one would be really funny?
The board's been sitting.
Angle of twist.
The boys were
Slightly moved.
So if you go back to that original expression that we had there, phi rather, is the angle of twist. That original, on the very first figure. So phi is the total angle of twist. In particular, phi, the angle of twist is measured, especially at the end. Right? So in other words, I'm not so much concerned about intermediate values of phi, I'm mostly concerned about the terminal value of phi, the phi at the end. How much is this thing going to twist? Because if it twists too much, the bolt comes off, or that kind of thing. So I'm mainly concerned about the maximum phi, that is the phi there at the end. But in reality, there's a distribution of phi. As you can see, phi is a function of x following the bar. So, okay, so far we assumed that phi of x was linear. So essentially what we're asking here is what if phi of x is not linear? Okay, everything we did so far assumed it was, that it was a uniformly distributed phi. So if we go back to the statement of shear strain that we had from last time, we said shear strain was equal to rho d phi dx. And that was shown in that second figure there. Rho d phi was the circumferential motion of the one side of the element, and dx is the thickness of the element. So that's where we got our gamma from. So if we rearrange that, we can say therefore d phi, an increment of phi along the length of the thing, is equal to gamma dx over rho. But we know that gamma, from as long as the bar is in the elastic regime, is equal to tau over g, right? Just the linear elastic region. And that tau is equal to the torque, which I'll make as a function of x, because again, we can be doing the Indian burn, right? So we have different torques at different locations along the length. Times rho divided by j, which also might vary as a function of x if it's not a uniform cylinder. So this is what we derived last time. Tau rho over j, or the shear stress. And the maximum shear stress was tau c over j, where c is the radius of the bar, because it occurs at the maximum of the surface. But again, I mentioned at the end, tau or t, the torque, and the polar moment of inertia, both could vary as a function of x if the bar is not uniform to geometry, or if you have multiple applications of torque. So plug all this together up into there, and we end up with an expression for d phi that is t of x over g of x, j of x, dx, because the rows cancel out. So, for any individual element, the amount of d phi that we get is the torque in that region divided by the modulus of the material and the polar moment of inertia of that cross-section times the dx thickness. And generally, obviously, so if we want to find phi, what are we going to do? We're going to integrate. Okay? This is the differential piece. So if we're going to find the total phi, the integral from 0 to L, whatever point on the length we're interested in, of that function, t of x over g of x, j of x, dx. Now, fortunately, most of the time, we're not going to have functionally distributed values. Most of the time, we're going to have discretely distributed values. Right? Like we did on the problem that we had last class. At the bottom problem, at one end it's a rod, at the other end it's a tube. I think the diameters are the same. Yeah. Nope, they're not. Anyway, one end it's a rod, one end it's a tube. So J is changing. But it's just changing discretely. The entire end of the rod has one value of J, the entire other end of the rod has a different value of J. Right? Torque is changing. There's an applied torque at the end, so that end experiences that torque, but then there's an additional torque applied by the wing thing there in the middle of the rod. But again, it's a discrete change. So in reality, most of the time, what we're going to say, what we're going to note is that the total twist is going to be the sum over I pieces. So that essentially, in those regions, in each of those regions, these are constant, are pulled out of the integral, and we just integrate dx for the length of that section. So we're doing discrete integrals along the length of the bar to yield the sum. Make sense? Okay. And this is where we get to the sign convention. For phi, it's positive when the right-hand rule for that phi points out of the bar, out of the rod, and it's negative when the right-hand rule points into the rod. So in other words, if you look at this, the picture over here, of the twist, the T on the bottom one, 527, the torque being applied on the outside is going to create a negative twist, because right-hand rule for that torque is my thumb pointing into the rod. You see that? But then, and actually the next one actually does the same thing. They both create negative twists. Okay, so there's a negative twist in both cases. Okay. On the top one, the outer one's creating a positive twist. 5.3. And the center one's creating a negative twist. So the total twist would be the outer one minus the inner one. Does that make sense to everybody? Okay. And twist matters because it's more going to, twist is going to be more of a design constraint. In other words, we want to know how much twist we're getting because we can only tolerate a certain amount of twist, or may not even be able to tolerate any twist. Okay, so let's quickly go, well, maybe not so quickly. Let's go through some problems, and then I'll go back and revisit that last one that we didn't get to last time, if we have time. I want to make sure we do the twist problems first, and then I'll go back and do 527. Okay, so let's do 549 first. An A36 steel axle is made from tubes AB and CD and a solid section BC. So there's a solid axle in the center and tubes going out to each gear. It's supported on smooth bearings that allow it to rotate freely. So in other words, there's no friction at B or C. If the gears fixed to its ends are subjected to 85 Newton meter torques, and you'll note that those are opposing torques. Determine the angle of twist of gear A relative to gear D. The tubes have an outer diameter of 30 millimeters and an inner diameter of 20 millimeters, and the solid section has a diameter of 40 millimeters. Okay. So, if we want to find the total twist, what are we going to do first?
So there, it's just, sorry, just to
Don't
make
step
sure I
on Blake's feet there. Go ahead.
Well, I just want to make sure that I'm doing what it's saying, correct?
Okay.
It's saying that there's just a rod.
There's a rod from B to C, a solid rod from B to C.
Okay. Then is it just like normally connected, or how is it?
Then it is presumably welded or something.
So
To
when
two
it twists,
tubes
it twists
from
the
A.
same way?
What's that?
When
Yeah,
it's
they're all rigidly joined.
Okay.
Yes.
So it's saying there's one is twist this way, one is twist that way.
Right.
And, okay.
So it's as if you were in a ZTR with a solid axle, rear motor, and you're doing this. So one is trying to turn forward, the other one's trying to turn backward to make you turn, right? And so there's going to be a net torque on the shaft connecting those two wheels.
We're looking for theta, right?
Phi, sorry, phi. All right, so we're looking for phi. So where are we going to start?
I'm gonna go with the free body diagram.
Go with a free body diagram, okay? So what free body diagram of what?
The whole A to D.
The whole A to D, the whole enchilada. Okay. So we have okay, nothing's drawn to scale here. There's our whole A to D. What else do I have to draw? Torque? Okay, where do you want to put a torque?
And we can
Okay, I'll draw the torques that are on the ends. This one's going that direction, 85 Newton meters. And this one is going the other direction, also 85 Newton meters. Really, I don't think it's bought us much.
What's that?
I don't think that bought us much, because it basically just duplicated our picture. What are we trying to find? Trying to find phi. So, how are we going to find phi? You probably use that equation that I intentionally left unerased when I erased everything else. Right? A little hint there. Except that's a sum. Right? So what am I summing to get my total phi?
Each segment, the two parts in the solid shaft. In the middle.
Right, so that's what I'm doing. Right, I'm adding up the phis for each of the three segments. And the nice thing about breaking it up like that is that AB segment is a nice uniform segment, BC and CD. So I can just use TL over GJ. Right? So it's going to be TAB, LAB over GAB, JAB, and so on. Do I know TAB, torque applied in section AB? So in the most rigorous sense, I would actually have to do a section, right, of the shaft here.
Yeah.
But by observation, we know that there's only the two torques applied. So we know that we have a uniform torque along there of 85 Newton meters.
Yeah.
Go ahead.
No, I just have a question. So this was question homework. I think I ended up getting it right, but I was a little unsure how it ended up coming right. So say we had two other torques applied in the middle.
Okay, so let's say B and C both had friction.
Yes.
Okay.
So how would we find the torque in the section BC?
In the center section.
In the center section.
So, yeah. So you find the AB section, you know what it is, right? So you're saying if you have unknown, you have reaction torques at B and C is what you're saying.
Well,
Is that what you're talking about?
we know what the torques are, but how do we cut it to find out what the reaction?
Okay, so if we know if there are reaction torques at B and C, we're in a little bit of a pickle.
Okay.
Because we don't really have a good way at defining the distribution of those reaction torques between B and C. Okay. So unless we have some other constraint. If we have a constraint, like we know that we know something about the twist between B and C or something, because we don't have, so in other words, if I section this here, right, I have this piece, then I know that the internal torsion inside of that member AB is 85 Newton meters, right? But then, if there were some other frictional torsion or something applied there that I don't know, it's an unknown, right? Then I don't really have a good way, let's say there's one here in the same direction or whatever. Then I don't have a good way of getting at this, right? It's indeterminate. But if I know this is 12 Newton meters, then when I section here, I know that the internal torsion within here is 73 Newton meters in that direction, because the total torsion on that member is 0.
Okay.
And I know it's 73 everywhere in between here.
So what if, say, it wasn't 12 on the other, say it was like 10? If you were to cut it and look at the other half, it would be different though, right?
No, because it all has to add up. So if this is 73, that would be 73 in here. And it's 73 all the way along. And let's say this is let's say this one's 10. right? Then I would, oh, okay, well then that's 10 and 12 is 22 and 85. That makes this one in here 63, again in that direction. And that one can't be 85. In fact, that one would have to be 63. Because the sum of all the torques, 10, 12, and 63 has to add up to 85. Okay. So in fact, if there was friction, and this was the drive end, then the back end would be experiencing less torque. Right, so you should, I mean, it's the kind of thing, you have torsional losses, like you should have talked about in principles at some point, the mechanical system. And that was dynamic usually, right? Most of the stuff you did there was some kind of, there was an omega involved, it was turning, right? But they're linear losses, they're resistive losses, if you will. Right, you guys remember that from, you guys did principles a year ago, so. I'm assuming, I don't know if principles was the same last year as it was 2 years ago.
I don't think so, but we had just gotten
Oh, you didn't have the mechanical piece, maybe, okay. Anyway, okay, but you understand what I'm talking about, right? Okay, so does that answer the question you had originally? All right. So now, we're back down where we were. Let's find V. Oh, well, we got tau AB. Or, I'm sorry, torque in AB. That's 0. And we just redraw the whole thing. And that's 85. Okay. So, do I know tau TAB? Do I know the torque in AB? And it is? Well, yeah, so look at the picture up there. It's easier to tell in the picture up there. So it'd be negative 85, right? So we have a negative 85 because it's causing a twist into the shaft. What about LAB? Do we know LAB?
0.4.
0.4. Do we know GAB? Some constant from the back of the book. You guys really ought to try looking this up in your book once in a while.
Mine doesn't have.
Oh, well, that's what happens when you buy the illegal international edition.
I didn't know it was international. I just saw
it. It's only when you
Cheap.
go in to sell it to us.
I just saw
I know. I didn't say it was illegal for him, I just said it was the illegal edition. Okay, what am I looking for? G, modulus of rigidity, or the shear modulus, 75 gigapascal. This is metric units, yeah, right, okay. So I've got G, 75 gigapascal. What about J?
Look that up.
No, not back of the book, not front of the book.
Google it.
Google it. Why do I even bother?
Pi over 2 times the radius to the 4th.
Close.
Right?
What's AB?
Is it hollow?
Read the problem.
Yes, it is. So
It's a
it's
tube.
pi over 2 times the outer radius to the 4th minus the inner radius to the 4th.
Right. So G is 75 times 10 to the 9th. J is pi over 2 times the outer, which is 0.03. Is that diameter?
Yeah, that's the diameter.
0.015 to the 4th minus inner, which is 0.01 to the 4th. That's my J. And then TAB you said was 85. And LAB was 0.4. And then everything's in SI units and I don't have to worry about the details. Right? Okay. What about TBC? What's TBC? center section?
It's gonna be 85.
Same 85, right, because it's 85 along the whole thing. What's LBC? 0.25.
Wait, I thought the first one was negative.
I'm just, they're all negative. So I'm just finding them all, and then we'll put the minus sign in front of the end.
Gotcha.
Next, it's all one continuous torque. There's no,
So even though they're going different,
they're both going into, this is why you count it as into or out of the rod. The one in the back is going this way, pointing back into the rod. And the one on this end is going this way into the rod. They're all pointing into the rod.
okay,
So they're all negative twists.
even though they're going in opposite directions.
Right, this is why the convention for twist is relative to the rod,
Gotcha.
not relative to some absolute geometry. Okay.
Gotcha.
Okay. Same thing with compression. We can get our minds wrapped around translational. This in translational sense, if I compress something, I say, well, it's got a negative stress. Okay, because the stress in this direction at the bottom, but it's in this direction, or at the top, but this direction at the bottom. It's a positive stress at the bottom, it's a negative stress at the top. No, it's a compressive stress. It's into the sample, so it's negative.
Gotcha.
Okay, but like I said, linearly, translationally, you can get your mind wrapped around that easier than you can rotation. Everybody good with that, the sign convention? Okay. So what's G for BC? It is indeed the same material. Everything's 836, so it's also 75 times 10 to the 9th. And what is J for BC?
Go with pi over 2 times whatever the radius is, 2/4.
Right, because now it's a solid cylinder, it's pi over 2 times 0.02 to the 4th. Right?
Would be 0.0.
That's the
Yeah.
diameter,
Oh,
0.04.
that's diameter.
So we have radius to the 4th, right, radius to the 4th power. Okay, what about CD, section CD?
Same as the first one.
Same as the first one, so I can just go in here and throw in a times 2. Save myself a little work. Right? And hopefully, that gives me a value of 0.0154, 34. If we trust the solution meter. Jesse's fingers are rapidly validating the performance of the solutions manual.
You're not rapidly, it's been long. But they are.
My thumbs don't work so well at 3:30 in the afternoon.
Hey, this is a soccer player who wears mitts over his hands.
That's right,
He doesn't have
exactly,
to,
exactly. He's not used to using his hands.
He should be typing with his toes.
Well, you're the goalie, aren't you?
Yeah, he is
Oh,
about
he's
using his
He
hands.
uses his hands, but he
Good
wears
point.
those, do you wear the big mitt things?
The mitts?
Don't
Gloves.
some
Those are
guys
gloves, they're-
like, yeah, but I mean, don't
You
some
can move your
people wear-
fingers.
Do they?
What, I don't know what you're saying.
All right, let's
There-
focus.
Like, aren't there some goalies who like wear like mittens so they can't move their like fingers? They just like,
No,
okay.
no.
You're dreaming.
Maybe that was
Yeah,
just
They're
gym
gloves.
class in middle school.
That's right.
Yeah, they're gloves.
All right,
Okay, that's what we did.
All right, we'll trust
in
this
middle
number.
school gym class.
because, anyway. And what's the units on that? Did you get there, or
Yeah.
Okay. same
Yeah.
number?
Yep.
Okay. What are the units? Nope. Radians. Right. SI unit is radians. So in degrees, that would be 0.879 degrees. So one side lags the other by almost a degree.
So how do you know which side is going to like, can you just be like, well, I'm going to call this my side that doesn't move, and this is going to be the side that will move?
No, it's relative twist. Twist is one end relative to the other.
Okay.
So that's why it asks for determine the angle of twist of gear A relative to gear D.
Right, but if you did D relative to A.
It would be the same.
wouldn't it?
Right, because it's relative velocity, or relative displacement, it's all the
You
same.
can't just pick which one. you
Yeah,
want to do.
displacement of A with respect to B is equal to displacement of B with respect to A. Actually, in most cases, it's minus the B with respect to A, but in this case, because the way we define torque, define twist,
Mhm.
they're equal, they're not equal and opposite. Okay? Snickering over there, Jason. All right.
I'm laughing about the thought in my head of trying to play goalie with mittens on. It's kind of,
Thanks, Gayla.
Sorry,
Look what
I saw
you
a
did.
really cool video that you'd appreciate. They played soccer in these big
Oh,
balloon things.
Oh, I love that video.
Yeah,
I was like, that's a sport I could get into.
that's pretty funny.
seeing King in soccer.
I've tried
Yeah,
really
pretty
hard,
much
I don't
it, yeah.
understand what's going on.
I'm sorry, I'm afraid I'd fall asleep before I actually.
Yeah.
Except for the girls did score 7 points last
7 goals?
Thursday.
Really?
Yeah.
I didn't see that. I saw they lost over the weekend, or on Wednesday, 1-0. Was it Wednesday? They lost to to Maradona. They lost to Maradona 1-0
They
in
lost to
overtime. Whatever. You know what I mean. They lost on Wednesday, 1-0 in overtime.
Yeah.
Okay, let's move on to 565. The 8mm diameter A36 steel bolt is screwed tightly into a block at A. Determine the couple forces F that should be applied to the wrench so that the maximum shear stress in the bolt becomes 18 megapascals. Also, compute the corresponding displacement of each force F needed to cause this stress. Assume that the wrench is rigid. Okay, so we've got this bolt, we're screwing it into block A, and essentially it's stuck. The bolt has come to a stop. And so we're trying to twist it, in this case actually out of block A. And we need to apply a torque to get it out, and it's going to require a shear stress of 18 megapascal in the bolt. Anything more than that, and we snap the bolt. Okay? So, and we wouldn't snap the bolt generally, unless it's defective, at 18 megapascal, I don't think. Who knows? So, what do we do?
Free body worked for us last time.
Free body of what?
Free body of, a handle. Let's
Well,
go
you
with
want
A.
just
Let's go with
the-
free body of A, 'cause we just want that.
Free body of bolt A. All right, here's bolt A.
Should only be the only one that had a letter next to it.
Yeah, right. Handle H, I don't know. Okay, there's our bolt. What forces or stresses or whatever are applied on this bolt? What do we have to add to the bolt?
A torque
You torque where?
on the top.
On the top? And how much is that torque?
Sorry, say that again.
How much is that torque?
2F times 0.1. Yeah, 2F times 0.15.
Okay. Or F times 0.3. 0.3 F. Right, that's the couple. The couple is the forces times the distance between them. Okay, actually I'm going to make that 0.3 F. .3 F. Okay. Good? So there's our free body. What do we do next?
Wait, isn't there
We would technically have a
reaction
react.
torque at the bottom?
Yeah, reaction.
So there would be a reaction torque at the bottom, also 0.3 F, because there's no other intermediate torques applied. What now?
F is just F over A. Right?
Well, it's not usually represented as F over A.
E,
Right, so it's usually shear stress, usually, well, yeah, it's in this context, we need to have something a little more elaborate than F over A. Normally it would be V, because it's the shear force divided by the A. If you have shear on a beam,
Gotcha.
okay? But here, we're talking about the maximum shear stress. And so it's a torsion, so we don't have a uniform shear stress at a point. We have a shear stress that depends on something. So you need to give me an expression for that in the context of torsion.
G times gamma.
What's that?
G times gamma.
G times gamma would be one way of expressing it, though we don't have a gamma yet. The values we got in here.
We also do, torque times phi.
At-
J.
Torque times what?
Phi, right? No, rho, it's rho, phi.
Actually, torque times C over J, because we're trying to find the maximum torque, which occurs at the surface.
Okay.
So we want to see the radius of the
So
of the shaft. Okay. But yeah, T times rho over J. So this is what we derived by using F over A and considering what is the context of F over A when in torsion. Right, so we derived that Monday, I think. No, Wednesday. We did that last time. I think we did that last time. Anyway. Okay, so tau max equals TC over J. What are we trying to solve? What are we trying to find? Trying to find T, right? So I can write this. Torque, we know, is 0.3 F. Right? Right, we already solved for the torque over here. So that's 0.3 F times C over J. Because it's asking for what is the force that I've got to apply. So I got to rearrange that and say then F is going to be equal to tau max times J divided by 0.3 C.
J's in the back of the book, which we just used.
J is not from the back of the book.
J's.
From the front.
J's equation is in the
Alright, so do we know tau max?
Yeah.
Do we know J? Or can we calculate it? Do we know C? And we got the 0.3, so we're good. Okay, so tau max is what?
18 megapascals.
18 times 10 to the 6th. What is J?
J is pi over 2 times.
Uh,
0.004.
So 4 millimeters to the foot.
That's not right. That's not drawn right. See what I'm saying? I mean, that's what they want us to do. But that's not the radius of the shaft. See what I'm saying? They've labeled that as the length of the shaft.
Well, they labeled it 80
Yeah,
millimeters as
80,
length, and then 8 millimeter diameter.
Oh, okay, okay. Oh, yeah, yeah, okay, I see, okay.
Those zeros.
Yeah. Okay, divided by 0.3 times, what's C? Oh, it's the same C. So I just make that a 3.
Wait, no. I thought C was the,
No, C is the diameter of the shaft that's experiencing torsion.
Okay, C is.
Or radius, I'm sorry, radius of the shaft experiencing torsion. Because it scales, remember, as tau rho over J, I'm sorry, T rho over J,
Mhm.
but tau max occurs at the surface where rho is equal to C, the diameter of the
Okay.
shaft. So this C is the diameter of the, or radius of the shaft.
Gotcha.
So that's the same C as we used to calculate J, but it was T to the fourth divided by C, we just knock out one of the C's.
I just thought C was different than the
C is the radius. Rho is the variable position within the radial position. Rho is a radial position. C is the absolute radius.
radius. Gotcha.
All right, after all that, we find that the force is equal to 6.03 newtons. Hopefully. Hopefully that works out. Okay? Okay, good. So that's our force. Is that all we need? What else are we supposed to find? I also compute the corresponding displacement of each force F needed to cause this stress. So what are they asking for? They're asking for phi. Well, they're, or they're asking for the displacement of F, but we're going to find that by finding phi. What expression are we going to use for phi, or how are we going to get the phi here? What's our approach for finding phi?
Just use our torque times our length divided by G, J. And then-
Because we only have 1 second, so we choose that. So the torque is 0.3 times F, so it's 1.89, I think. No, 1.8, sorry. 1.809. Times L, which is 0.08, divided by G. What's G?
It's the same one, so it's 75 megapascal. Gig,
Mega, giga, mega, giga, 1, maybe, yes, right. It's giga, that's yes. Times, J we already found, pi over 2, from 0.004 to the 4th power. That gives us a phi of 0.00480. What are the units of that again? Radians. So how far does F move?
So we have to find this arc length.
How far does F move?
So you draw the triangle,
Draw the triangle.
not like you draw a triangle and you put the radian angle in it. And then you know the 150, and you run by the other part that you didn't draw.
Is that what you're saying?
Mm-hmm.
Okay. Or you can just recognize that S is equal to R. Right? It's conversion from polar coordinates to V equals R omega, or V equals R omega, S equals R phi, you know, okay. So it's just that times the radius.
So are we considering the rotation being negligible? Consider it straight?
No, this actually is the arc.
Oh, that is the arc length?
Right, if you think about it, if it moves in a full circle, right, what would it be? It'd be R times 2 pi. 2 pi r, the circumference of the circle. Okay, so this is the circumferential motion. It is not the translational motion. But for such a small angle, it might as well be the translational motion. And if we do that, we get 7.2 times 10 to the minus 4, which is equal to 0.72 millimeters. So in order to create 18 megapascals of torque, or of shear stress on that bolt, I only need to move it less than 3/4 of a millimeter. Okay. So I've taken the time to go through in class in the lecture part to try to derive these things. You guys are going to end up just using these expressions on the homework, right? Phi equals TL over GJ, tau equals T rho, typically T rho over J. But in reality, you need to understand where that came from. You need to be able to sort of wrap your mind around it. Because if you wrap your mind around it, you're more likely to remember it when you're taking fundamentals of engineering exam. Right? You can, oh yeah. I mean, you'll have a cheat sheet. In fact, I was looking today to find out what equations they give you on the FE exam. I figured I'm going to give you guys the same equations on the test as they give you for the FE exam. So I'm going to go through the FE exam for strength of materials, see what equations they give you, and I'll give you that equation sheet, okay, for the exams. But otherwise, the exam is a big closed book. But you don't want to be rifling through reference, looking up exams or looking up equations all the time. Right? You want to be able to conceptually get them so you can remember, oh yeah, that's because that's F over A, and yeah, I remember now, and be able to get to this. So I walked you through that process in the notes, and we'll continue to do that through the semester. I'll walk you through where this comes from. In the end, from an engineering standpoint, you just use sort of the final product. But if you really understand where that came from, if you make sure you conceptually get it along the way, it'll make it easier for you to recall and work with those problems once you get them. Okay? Make sense? All right. So we have 5 minutes. I'm going to go back and try to work through at least that second problem there. 527. So here we have another shaft with 2 torques applied, one at the end, one in the center. The rod and the tube are made of material having an allowable shear stress of 12 ksi. Determine the maximum allowable torque T that can be applied at the end of the rod, and from there the couple forces P that can be applied to the lever arm. Everybody understand that? So in other words, torque T is going to cause a shear stress of 12 ksi. But then that shear stress, I mean, by virtue of the way that they're asking the problem, you can presume that that shear stress is going to occur in member AB. The maximum is going to occur in AB. And that in fact, BC might not have achieved its full shear stress. So you might be able to apply an additional shear on section BC. Does that make sense? Kaylee, you see what I'm saying? So in other words, we're going to find the stress out here that's going to cause this to reach 12 ksi. But this one shouldn't be at 12 ksi then, so we should be able to tolerate some additional torque on these wings to put that one to 12 ksi. Okay?
So the inner portion, the tube part, would it get stressed out before the outer part?
Which gets stressed out first? Outer or inner?
Outer.
Got to vote for outer. Blake's the one asking, so I'm assuming he's not going to vote. What do you guys think? On that tube, which is going to be see the more shear stress, the outer or the inner? Not. Yeah, so the torque is actually applied sort of at the end. The torque, you don't think of the torque actually being necessarily something grabbing and twisting. It could be something like this twisting. It could be a frictional torque. You don't know that. But it is the outer. All right, look at our expression for shear stress. tau C, or rho.
Oh,
J.
you're talking about just the outer, okay. I was talking about the solid with, compared to the,
Right, so the solid compared to the other one, we got to take into account the J's to figure out which one's going to experience the larger. Right, whichever one has the smallest J
yeah,
is going to have the largest tau.
okay.
Right, the smallest inertia is going to give you the largest tau. Okay, and so AB has a rod of 2 inches, and BC is 4 and 2. So J for AB is going to equal pi over 2 times, did they give me diameters or radii? Times 1 inch to the 4th power. So it's going to be pi over 2. J for BC is going to be pi over 2 times the outer 2 to the 4th power minus the inner to the 4th power. So I end up with 15 times pi over 2. You see how this is the J's? So the J for the BC, the tube, is 15 times as big as the J for the solid rod. See it?
Yeah, I guess,
So if the J is bigger, then the tau is smaller.
but isn't the torque different?
Not initially.
Oh, because we're saying initially P's are 0.
Right, we're saying initially the P's are 0.
Oh, okay, gotcha.
Right, so we're finding out the torque, because it says find the allowable torque T that can be applied to the end of the rod. And from there, find the couple P that can also be allowed.
Gotcha.
Okay? So initially, it's just, even if they were both applied simultaneously, you can still do it by superposition. You take the outer one first, find out what its effects are, and then add to that the effect of this one, because the wings are not going to have any effect on AB.
Yeah,
They're only going to have an effect on BC.
and that's why I thought that BC would break first, I guess, what I was
Yeah.
have a higher.
If BC were made, yeah, but BC has a much higher, much larger inertia, so it takes a lot more torque to get it to that. So we didn't get that far working through the problem, but at least we got some kind of a concept covered there. All right?
So wait,
Go ahead.
I'm trying to think how to say it. So, you guys J's in the denominator. The torsion will be larger when J is smaller.
The shear stress will be larger when J is small.
Yeah, sorry, shear stress is larger, J is smaller. So how would we do this problem if they were the same material? Because you wouldn't know which one.
Well, if they were the same material, then you couldn't tolerate any P. If they were both the same, if it was a solid rod going through there.
Gotcha, because you
Because-
log.
Right, whatever T was to cause failure, it would be causing failure along the entire length of the rod.
Okay, so. Okay,
Okay?